Good afternoon, everyone. My name is Dr. Kim Tait. I'm the Tech Endowed Chair of Mineralogy at the Royal Ontario Museum. I'm so delighted that you're able to come today for our Curator Conversation, a digital program that explores themes and subjects from ROM collections alongside industry professionals. I'd like to first begin by acknowledging that the ROM sits on what has been the ancestral lands of the Wendat, the Haudenosaunee Confederacy, the Anishinaabeg Nation, including the Mississaugas of the Credit First Nation since time immemorial till today. Today's Curator Conversation celebrates the NASA OSIRIS-REx mission to Bennu and the unique opportunity it gives us to learn more about the past, the present, and the future of life in our solar system. I would love to welcome, first of all, Dr. Tim Haltigin to the program. Tim is a senior mission scientist in planetary exploration and acting manager for planetary science and space astronomy missions at the Canadian Space Agency, where he leads Canada's efforts in exploring the solar system. He received his PhD from McGill University, where his research revealed similarities in the evolution of ice-rich terrains on Earth and Mars. He was previously in the running to become Canada's next astronaut, has worked on a variety of robotic missions throughout the solar system, and has an asteroid named after him, 130066 Tim Haltigin. Tim currently serves as Canadian Mission Manager for OSIRIS-REx. So Tim, thank you so much for being here. And I just have to say that Tim is one of my favorite space people. So this is going to be a lot of fun. We've been working on this mission for a while, and I just want, maybe to start with is just tell us a little bit about OSIRIS-REx and what's happening.
No, for sure. And thanks so much for allowing me to be here. And thanks so much for the invitation. I'm super excited. So the mission, OSIRIS-REx, you're right. We have been working on it for an awfully long time. This is a mission that is led by NASA. And the goal of the mission is really neat. It's to take a spacecraft and fly out to an asteroid with a bunch of science instruments on board to help us understand its shape a little bit better, what it's made of, how it's flying through space. And so really giving us a better understanding of how asteroids are formed and how they work. But what's really exciting is that this is also a sample return mission. So the spacecraft was able to collect a sample from the surface of the asteroid and is due to bring it home unbelievably a week from Sunday. And as you said, I mean, this is a mission that started in 2010. And so there's been just hundreds of thousands of person hours that have gone into all of the planning. And here we are just over a week away from having those samples back on Earth. It's incredibly exciting.
So both you and I were actually at the launch in 2016. So do you want to talk a little bit about that? I certainly personally felt that was really life-changing for me, but I'd love to hear your perspectives on that.
Oh, for sure. It's something I'll never forget, honestly, the rest of my life. So it was a perfectly beautiful cloudless day at the Kennedy Space Center in Florida in the US. And there we were sitting, across the water, and we saw the rocket with our, the little payload on top of the spacecraft. And, you think about, this was in 2016, right? So at that point, 6 years of work had gone into designing and building the spacecraft and testing it. And there it was sitting on top of a controlled explosive, and everyone was, really hoping that it would go the right direction. And indeed, it was an absolutely perfect launch. I think less than a second into its designated launch window. So everything went flawlessly. The rocket took off, and there it was off on its way. And so it's really neat. So the spacecraft itself, it took almost 2 years to fly and catch up to the asteroid. So after its launch, it had to go all the way around the Earth, or around the sun once, and come back to the Earth. And it actually flew underneath the Earth and shifted its orbit a little bit to go chase down this asteroid. And so it ended up flying close to 2 billion kilometers. And then finally in December of 2018, so just over 2 years later, we finally arrived and opened our eyes and turned on the cameras. And I think the image you're seeing on the screen there is what we saw, which was this incredible rocky body that was a lot rougher and scarier than we had all anticipated, I think. And so we ended up spending about 2 years using the different instruments on board. So we had cameras again to help us see what it looked like, and we had tools called spectrometers that measure the type of light that bounces off the asteroid to help tell us what it's made of. And also a Canadian instrument called OLA that helped us really measure the shape very, very, very accurately. And so by putting all of this information together over the 2 years, we did an incredible job. The team did an incredible job of better understanding the geology and the makeup and the history of the asteroid, but also using all of that information to help us pick where we could navigate the spacecraft to safely in order to collect a sample. And so finally, after months and months of rehearsal, we managed to collect a sample in October of 2020. So this is now 4 years after launch. We made it on the first attempt. It was incredible. And so the spacecraft collected roughly 250 grams is the estimate right now of the material. And we had to sort of hang out in space for a while before we could fly home. So it wasn't until May of 2021 that the Earth and the spacecraft were in the right position to start flying home. And yeah, it's been on its way home ever since. And next Sunday, here we go. There's going to be a capsule landing in the Utah desert, and we're just tremendously excited for it.
So you mentioned something about Canada being participating in this mission. So can you tell me a little bit more about, how Canada helped with this mission, and a little bit about the Canadian Space Agency's role in all this?
Yeah, so again, this is a mission that's led by NASA, but has had significant Canadian contribution to it. So one of the things we're incredibly proud of at the Space Agency is our ability to support Canadian scientists from around the country on the science team of the mission. So yourself included, and other researchers from around the country, we've been able to ensure that Canadian scientific contributions have been made to the mission from the very beginning. But it's not just our scientists, it's our industry and it's our hardware as well that we were able to highlight on the mission. And so one of the science instruments on board is called the OSIRIS-REx laser altimeter, or OLA. And this, the technology works very similar to sort of, the laser rangefinders that you can pick up at Home Depot, right? You fire a laser and it bounces off the wall and comes back and basically measures how far away that surface is from your laser. So it's actually a very similar technology. We had 2 lasers inside of the instrument that were able to operate from different distances away. And essentially what it did is that it fired the laser and measured very accurately the time it took for the laser to come back. And so you're measuring distances. But what was really neat about this one is that there was a mirror inside as well that could direct the beam. And so it oscillated, sort of moved back and forth really, really fast. And so essentially what we did is we almost painted the surface with laser points, and we ended up collecting, I think it was about close to 3 billion individual measurements of the shape of this asteroid. And so by putting all of that data together, what we were able to do is we were able to build up a detailed 3D model of this asteroid. And so when you think about this asteroid as being 500 meters across, or so, roughly the size of the CN Tower, let's say, we understand its shape down to 1 point every probably 4 or 5 centimeters, which is just incredible. And so that was all with Canadian technology. And so the reason that type of data is really important is for 2 things. One is just the pure science of it, right? So understanding any type of geology, you've done geology out in the field and with samples, understanding the shape and the makeup are 2 very important things. And so the shape tells you a little bit more about the makeup can tell you about the shape. And by putting those pieces together, you really get a better sense of sort of just the geological history of the body. But also, we needed to find a place where we could safely get the spacecraft down and collect a sample. And so it was OLA data and that 3D model that really allowed us to make sure that we could find a place to collect a sample. And so, we contributed all these things to the mission, which was wonderful, and we've done incredible science for the last number of years. But what's also tremendously exciting for me is that Canada is going to receive a portion of the sample that comes back to Earth. And so this is the first time that Canada has been involved in a sample return mission. This makes us only the 5th country on Earth to be receiving materials from outer space from a sample return mission. And these are samples that we're going to be able to make available to generations of Canadian and international scientists. And so, to me, sample return sort of like the gift that keeps on giving, right? We've done some wonderful science up to now, and we'll do some wonderful science in the coming months and years on the sample that's returned. But we also get to do decades and decades and decades of work on this as well, which is really neat.
Wow, there's so many questions I have here. So one of the things that I don't think people understand is that, OLA was built right here in the GTA. Do you want to talk just a moment about that? Because I really want to give the shout out to, not only Canadian, but, GTA and local science and engineering that's happening.
Absolutely. So OLA, the prime contractor was a company called McDonald Detweiler and Associates MDA in Brampton, and our technical lead was a gentleman named Dr. Cam Dickinson, who is a wonderful scientist, an incredible engineer, and just a good person as well. And so Cam helped lead the technical team through years and years of design and development, and things were definitely not always easy. We ran into all kinds of problems during the design and build. We broke components during the testing and had to sort of do redesigns. But it was an incredible performance by the full MDA team, in order to produce an instrument that worked. And so in lockstep with the technical development was also the science development as well. And so it was a gentleman named Dr. Mike Daly from York University, who led the science team for OLA. And so, OLA definitely has its roots in the GTA and fingerprints all over it for sure.
That's fantastic. So we're having a look at the surface of Bennu. So can we talk a little bit about why Bennu was selected as an object to go to? I mean, from what I've learned about space, there's a lot of different objects that could have been selected. So why Bennu?
For sure. No, there's what we know of right now, I think there's something to the effect of over 500,000 known asteroids. And so getting from 500,000 choices down to one was a pretty interesting process for sure. So there were a number of things that went into it, both scientifically and from an engineering standpoint. So on the engineering side, I mean, when you think about a sample return mission, there's only so of these 500,000, there's only a certain proportion that are sort of in the right orbit that you can send a spacecraft to in a reasonable amount of time. So that was sort of step one. And then of those that you can send a spacecraft to, there's only a smaller number that you can send a spacecraft to and back, because being a sample return mission, we had to turn around and come home. Of those ones that you could get there and back, there was only a handful that were big enough. And the reason that size is important is that small asteroids tend to spin a lot faster than big asteroids. And so if there was an asteroid that was too small, it would spin too quickly and make it way too challenging to try to get a spacecraft to interact very softly with the surface. So it had to be big enough. And then of those, there was a handful that were made of the sort of really interesting scientific materials that some of the stuff we were most interested in. So asteroids can be made of lots of different things, but this particular asteroid, what we knew about it is full of carbon and carbon-rich compounds, which allows us to answer some really, really neat science questions. And so, where can we get a spacecraft to? Where can we get a spacecraft back from? Which ones are big enough? And which ones are sort of these carbon-rich ones? And that brought it down to about 5. So from 500,000 down to 5 individuals that we could choose from. And Bennu also is really neat in terms of its orbit, that it tends to come really, really close to the Earth. And so this is one of the ones that we really wanted to learn more about how it was flying through space in its orbit. So ultimately at the end, that's the choice we made.
Fantastic. So you mentioned carbon. So as a scientist, I'm certainly interested in the carbon-rich rocks that are on this asteroid. So can you talk a little bit about that and why somebody like me or, even the general public would be interested about a carbon-rich asteroid?
Sure. So the O of OSIRIS-REx. OSIRIS-REx is actually a long acronym for Origins, Spectral Interpretation, Resource Identification, and Safety Regolith Explorer, which ties back to all of the science objectives that we had. But it's that O that's particularly fascinating, the origins. So asteroids themselves, they're really, really neat bodies. You know, I think a lot of people think of asteroids as just these, you know, lumps of rock that are flying through space, and, you know, they're kind of boring because there's no atmospheres and nothing living on them and stuff like that. But asteroids are actually, you know, you can think of them almost like cosmic time capsules. So way back at the beginning of the solar system, it was, you know, about 4.5 billion years ago, there were no planets. And just as the sun was forming, there was this big swirling disk of dust and gas. And, you know, these bits of dust would bonk into each other and sort of stick together. And then bigger bits would come and collide and run into each other, and so on and so on. And that's really how the planets were formed. It's just this accumulation of material that kept sort of colliding with each other. But not all the material made it into planets. Some of the leftovers were, you know, I sort of think about it like when you're cooking, right? You're mixing all your ingredients, and yeah, most of the stuff goes in the bowl and you're fine, but there's little crumbs and leftovers on your counter, and that's what an asteroid is. And so this is material that's, you know, it's sort of the raw ingredients of planets, and they haven't really changed over the last 4.5 billion years or 4 billion years. And so going to get a piece of an asteroid is sort of like going back in time by 4 billion years to understand what the materials were at the very beginning of the solar system. So all this back, there's your O, your origins, right? What was there at the beginning of the solar system? And what we've learned from other asteroids and from meteorites that have landed on Earth is that there's these carbon-rich compounds. So carbon is a really neat atom because it sort of serves as the backbone for organic molecules, or things that go into life. So carbon bonds with, you know, hydrogen and oxygen and makes these really cool chains. And really, what we're learning here is potentially, you know, where did life come from, or the building blocks of life come from, which to me is fantastic. One of the theories out there is that early Earth, as it was forming, was bombarded by some of these asteroids carrying these amino acids, or these organic materials. And you can think about it almost as the Lego blocks of life. They combined with other things on Earth that eventually turned into life. And so if we're able to look at some of these compounds from 4 billion years ago, we can really potentially understand, you know, where life came from in the first place.
But we already have rocks coming from space. This is the natural process that is bringing some of these. So, you know, why did we go out there and collect some of this material from Bennu?
No, it's a good question. You're right. So there are, you know, the Earth is bombarded with, in fact, tons and tons of material every year. Meteorites are falling all the time, various sizes and shapes and things like that. And so you would think, well, if we have tons of material coming from space, why would we go and fly an entire mission just to bring back 250 grams? And so there's a number of reasons. One of them is we know exactly where we were able to select the material. We know exactly where it's from. So meteorites, we don't get to pick where they fall from, right? It's just random bits of rock that happen to be in space that land on Earth. And so we don't know where they came from. And not knowing where they came from, you know, allows us to tell some general things about the history of the solar system, but not specifically. So that's the first thing. But the most important one is what happens to that rock as it flies through the atmosphere. So meteors, as they come into the atmosphere, anything flying in is going to get really, really hot. So you actually sort of burn the outside of the meteorite, which changes the chemistry and really changes a little bit of the materials. The other thing too is that meteorites on the ground have probably sat there for a while, and so there's a lot of contamination from Earth things. So there's terrestrial water that's got into it, potentially, you know, things growing on it and things like that. So it's not pristine. So the reason we went to do the sample return mission is we got to choose where we got the material from, but we're also able to keep it perfectly pristine. So it's this getting the clean, unchanged material from 4.5 billion years ago that allows us to study it. And that's why it was so important to get this very clean, very pristine, and keep it very safe from contamination material back to Earth.
Awesome. So yeah, there's a picture of the clean room down at the Johnson Space Center where this material will be. So they're wearing suits. Do you want to talk a little bit about that real quickly? Just how they'll
Yeah,
handle
so the capsule itself, so the sample is inside a very protected capsule right now that's part of the spacecraft. And so as the spacecraft is approaching Earth, early on next Sunday morning on the 24th, it's going to release this capsule, and it's only the capsule that's going to come and land in the desert in Utah at the place called the Utah Test and Training Range. And the spacecraft itself, with all of the science instruments, is actually going to stay in space and will do a maneuver and actually go chase a new asteroid. But it's this capsule that you can see on the screen now, inside of which is the sample. So what's going to happen is there's going to be a specialized team that's going to come and recover this capsule and bag it, sort of triple bag it and contain it and take it to a clean space at the UTTR, the range in Utah. The next day, so Monday, I think the 25th, this is going to be transported then to the Johnson Space Center in Houston, where a very specialized room has been constructed. And this room is incredibly clean, as you can imagine, because the last thing you want is to do all of this work and bring back this pristine material from outer space and then just contaminate it with Earth microbes and water and things like that. And so the room itself and all of the containers in which the sample will be placed are very clean. They have actually nitrogen gas going through them and to make sure that nothing's going to react with them and change the chemistry. And all of the incredible precautions are going to be taken to make sure that we keep this material as pristine as it was when it formed back in over 4 billion years ago.
Awesome. So I've monopolized your time here and asking questions myself, but we do have a lot of attendees that are asking questions, and I'm going to warn you, there are some really good questions that are coming through. So I hope you're ready.
I'll do my best.
So one of the questions is, how do you know that it has high carbon if you haven't sampled it yet?
Great. So this is really neat. So the families of asteroids that we know of these 500,000 or so asteroids we know of, we're able to study them at a very coarse resolution using Earth-based telescopes, for example. And so using special spectrometers or these tools that allow us to look at sort of the light that bounces off the asteroids, we can tell a little bit about what they're made of. So that's part one. Part two is we have, as we mentioned before, a lot of meteorites that have come back to Earth from these asteroids. And so we've been able to do very specific measurements on the meteorites to identify some of these carbon compounds. And so by combining sort of the light, the spectrum, as it were, that we can find from Earth-based telescopes and what we know about meteorites, Bennu was shown to have a very distinct curve that we know is associated with carbon compounds. And so that was from a bulk. And then once we got there, we used some of the spectrometers on board as well to look at the chemistry of the surface materials. And indeed, it was confirmed that it was going to be carbon rich. So we're very obviously, until we analyze it on Earth in labs, we're very confident. All the data suggests that we selected the right asteroid and the right place on the asteroid to sample.
So there's a question about other sample return missions. So there have been other asteroid material returned back from the Japanese space agency. So do you want to talk about how that sort of plays into what we know about the body and what we hope to learn, and maybe what is a little bit different about this one?
Sure. So JAXA, or the Japanese Space Agency, has actually run 2 sample return missions to different asteroids. So these were missions called Hayabusa and Hayabusa 2. And they went to different types of asteroids and have returned material that have allowed us to, to learn some of these amino acids in these organic molecules, for example, looking at sort of prehistoric water molecules that have been locked in the mineral grains and things like that. And so part of what we're doing, though, we're going to an asteroid that's slightly different in composition, or what we think is slightly different in composition. And so playing the compare and contrast game is also really important as well. So what we can learn from one asteroid is certainly valuable, but what we can learn from the other one, and then understanding why it's the same or why it's different as other asteroid materials out there in space, really helps us to then understand, or at least project, what we think these whole families of asteroids are made of, and why they're different.
There's so many good questions. I don't even know which one to ask next, but I'll do this one. So they're talking, I mentioned nitrogen gas is going to be used to surround the sample. So one of the attendees is asking, why nitrogen?
Well, the great thing about nitrogen, so I'll back up a second. So if we were just to expose this material to regular Earth atmosphere, there's a lot of water, right? There's water vapor everywhere you go on Earth. And so one of the last things you ever want to do is allow water to interact with the material that was pristine, because that's when a lot of chemical changes can happen. And so instead of exposing the sample to regular Earth atmosphere, the reason we want to keep it sort of bathed in nitrogen is that it stops any of those reactions from happening. So nitrogen doesn't really react with any of the materials that the rock is made of. And so it's a way of keeping it clean and keeping it pristine, as long as you have it under this pure nitrogen atmosphere. So again, it's not the room that's going to have nitrogen, because you still need the scientists to be able to breathe. So there's a very, very clean room, but then there is an even cleaner box inside of that room that's flooded with nitrogen that the scientists will be able to work within.
Yes, Earth air is good for our skin, not good for rocks.
That's correct. Yes.
Part of the theme. So one of the questions, which is great, is what are the specific tests, and what will we be doing with the samples after they come back?
Oh, there's a lot. There's a lot of different types of analyses that we can do. Let's think. One of them is sort of physical materials. So how strong are asteroid materials? How resistant are they to force and things like that? So just understanding the physical properties of some of these materials will allow us to get a better sense of, the physical properties of asteroids as a whole, but also, how rocks are formed in the first place. And so, they're physical elements. There's going to be a lot of chemistry done in terms of what types of minerals are we finding within this sample. Kim, as you well know, I mean, this is, you think 250 grams doesn't sound like an awful lot, right? But the reality is that micrograms of this material, like individual grains or two, are enough to make tremendous discoveries and inferences about the origins of the solar system. And so understanding the minerals, what types of rocks were able to form, or what types of minerals were able to form, will tell us about the history of the solar system. So there's going to be a lot of chemical in mineralogical analyses. And then the organics, right? What type of organic materials are in there? Are they the same as the amino acids that we know on Earth now? Or are they different? And if they're the same, why? And if they're different, why? And so it's each of these questions that's going to generate, 5 more questions and just feed this sort of generations of research to come.
I always use the analogy of the Apollo rocks, right? So we brought back material, from the 60s from the moon, and they're still making, all of it, scientists, because there's such a change in technology, decade on decade, we're still making really important observations and, science-worthy, measurements on the material that was brought back 50 years ago. So, as you say, this is going to be not even just our lifetime, but lifetimes of science that could happen on these rocks.
For sure. I mean, think about it's not just the technology, right? So obviously there's been huge advances in technology in the last 50 years. I mean, heck, think about just how your phone has changed in the last 5 years.
Right.
Never mind how much laboratory instruments have changed over the last 50 years. So there's been a huge technical advance. But we also have a way more mature science community, right? We've been asking 50 years of questions that allow us to ask even better questions. And so, yeah, we're doing things on the Apollo samples right now that we couldn't have possibly measured because the technology wasn't there. But we're also asking questions that we didn't know how to ask 50 years ago. And so to me, that's, as you said, this is why it's not just about the science we're doing in 2023 or even 2033. This is about what type of science are we going to be doing in 2073 and 2083. And so, you know, kids in elementary school and people that aren't even born yet are going to be making incredible discoveries on this stuff. So that's part of the reason I'm so proud that we're part of it.
Well, that's the exciting part. You and I actually did a lecture to a bunch of grade school kids about this mission, and I think that's just really exciting. Is that, you know, these are the scientists of the future that we're speaking to, that will be making these observations, not just us. So that is so exciting. One of the questions is talking about Mars sample return, and that is another project that we have been working on together. And so just asking a little bit about how this is preparing us for future sample return missions.
Sure. So there's a lot of things we can learn from a mission like this, and in fact, there's a lot of things that are different as well. So part of returning any material from anywhere in the solar system is tremendously complex, right? You need amazing engineering, you need things to go well, you need a bit of luck, and everything needs to come together. So in terms of what can we learn from sample return missions, we know better how to navigate spacecraft, how to use different instruments to select materials that we would want to bring back, that we'd be interested in, some of the technologies in terms of the landing and the recovery efforts. How do we make sure that we do all of that safely? So there's a lot of things that will feed forward from a mission like this into the eventual plans for Mars sample return. Now, that being said, Mars sample return is quite a bit different in the sense that the material itself, so asteroids we know are horrible places for life itself, right? Great for the building blocks of life, but terrible for life itself, right? There's no atmosphere, there's no liquid water, it's bombarded with radiation, horrendously cold, like just an awful place for anything to grow. So we know that asteroid materials, there's no chance that there's going to be anything living. Now with Mars, the rocks that we're bringing back from Mars, even though today Mars is a terrible place for life at the surface, 3 billion years ago, 3 to 4 billion years ago, the conditions were actually a lot more similar to those on Earth. Lots of liquid water, nice thick atmosphere, warmer temperatures, and the type of place where life could have formed, not just these organic molecules. And so the precautions that we would need to take for Mars sample return are then not only ensuring that we're keeping the sample clean from terrestrial contamination, but also making sure no one believes that we're actually going to be bringing back anything alive, but the precautions we take will be a lot tougher to meet for sure for Mars sample return.
And not only keeping the rock safe, or the human safe or the planet safe, but also keeping the rock safe, right? So I always think of it as like a two-way street, right? We want to make sure that if we do find any signal of life, we want to make sure that it is from another planet, not from, you know, me sneezing on it or something like that, right? So that's always
exactly. And the thing too about the samples that we're bringing back from Mars is a tremendously dynamic planet. Lots of processes that are similar to Earth, or there were. So there were rivers flowing and lakes developing and volcanoes going off and all sorts of things that don't happen on asteroids. And so the suite of rocks that we're planning to bring back from Mars allow us to ask very, very different types of questions. So as a planetary scientist, fundamentally, everything we do comes down to two questions, right? How do planets form and evolve over time? And did life originate anywhere other than Earth? And so the origin part, asteroids are perfect for, right? They're the raw materials of the planets. But understanding the evolution of planets and how they change in some of those processes, these volcanic and sedimentary rocks that we're going to be able to bring back from Mars are complex in a way that the ones from the asteroid aren't. And so we'll be able to answer a fully different suite of questions that will allow us to sort of piece together the whole timeline of the solar system, not just the beginning.
So I think we have time for one more question. This is a good one. It's asking, we've spent, billions of dollars on this mission, we as in, humanity. How are we going to decide who gets to study them, or, how are we going to distribute them amongst the scientists to make these discoveries?
Yep. So that is a great question. It's because obviously these are invaluable, right? I mean, we cannot go and collect another another sample like this, and so we're going to have to be really, really careful about who gets to work on them. So the way that we've set it up right now is that 25% of the material that's brought back is going to be made available to the current science team to answer some of the questions that we had been asking from the very beginning. So these are the samples that we're going to need in order to meet all of the objectives that we had for the mission. Again, 4% of the material is going to come back to Canada, and 1% of the material actually is going to go to Japan as well, in exchange for some of the Hayabusa 2 material. But what that means is that there's over 70% of the material actually that we're just going to lock up, and we're going to keep perfectly untouched for years and years and years and years and years, to make sure that we don't inadvertently change something, and to allow us to do some of these analyses 20, 30, 40 years from now. And so in terms of who gets to work on it, who gets to decide, again, for the first while, it's the current science team of the mission. But moving ahead, the plan then is to run competitions periodically, where scientists from Canada and from around the world can apply to work on the samples, and we'll have a full panel of scientists and managers and curators that will make an analysis on whether this bid to work on the sample will, return high enough science for the amount of material we need to use. And so there'll be decision making, but constant curation, and Kim's, curating a sample and curating a collection of samples. You're very interested in the science, but you're also very interested in preserving material to do generations of science. And so that's the tack that we're going to take.
It's always so tricky because you want to preserve the material and keep it, as it was. And, that's what we do at the ROM, is we always have this real desire to protect the material, but at the same time, to understand the material, we have to, use some of it to do the scientific analyses. So it's this constant back and forth of how much to do, and but as we get better and better at science, and using smaller and smaller materials to make measurements, then we can already make these measurements. So anyways, thank you so much, Tim, for your discussion today. I had a lot of it was great, and I'm getting some great messages in the chat thanking you. So on behalf of the visitors that are online, thank you for your time. And I really hope that everybody can follow along on September 24th. Both Tim and I will be in the United States waiting for this material to arrive. Tim will be at Utah Test and Training Range, and I'll be meeting him at the Johnson Space Center for the material to get there. And but you can watch NASA TV on the day of, and they'll be doing a lot of interviews and discussions about what is happening. And we're really hoping to do this live at the ROM. So we're going to have NASA TV playing for people. So if you want to come down to the ROM that day and learn a little bit about OSIRIS-REx, we've actually 3D printed Bennu, so everybody can come and hold Bennu and learn a little bit about the landing site, which is a little sticker here on top, and talk to some of our docents and volunteers that will be on site to answer questions. So I invite everybody down here on September 24th. If you can't, definitely tune in live on NASA TV, and we look forward to sharing the good news that the sample has arrived safely on September 24th.